Hi, I am Bhumika from BSc Honors First Year Chemistry. In this video, I am going to read alkynes. Introduction. Alkynes constitute another series of open chain unsaturated hydrocarbons having the general formula CnH2n-2. As the formula suggests, they are even more unsaturated than alkenes. They contain a triple bond between two carbon atoms in their structure and are isomeric with dienes which contain two carbon-carbon double bonds. In the present chapter, we shall consider the chemistry of alkynes. Nomenclature. According to the common system, alkynes are generally named as derivatives of acetylene, though some of them have special names as well. In the IUPAC system, the names of alkynes are obtained by adding the suffix "ine" to form the word. The other rules have been already explained. The common as well as IUPAC names of first even alkynes are given as below. Common name acetylene, IUPAC name ethine. Common name methylacetylene or allyline, IUPAC name propyne. Common name ethyl acetylene or alpha crotonyline, IUPAC name 1-butyne. Common name 1,2-dimethyl acetylene or B-crotonyline, IUPAC name 2-butyne. If a molecule contains both carbon-carbon double bond and triple bonds, the two are treated as par in a seeking the lowest number combination. However, if the sum of the numbers turn out to be the same starting from rather end the carbon chain, then the lowest number is assigned to C double bond C. Alkynyl groups. The monovalent group detained by the removal of hydrogen atom from a molecule of alkyne are known as allynyl groups. The individual groups are named by replacing the final electron of the name of the alkyne by YL. For example, ethanoline and 1-propanoline. Structure isomers in alkynes. Alkynes exhibit the following types of structure isomerism. First, chain isomerism. Alkynes containing 5 or more carbon atoms show chain isomers. Position isomerism. Alkynes having 4 or more carbon atoms can exist as position isomers. Functional isomers. Alkynes have the same general formula as dienes. Therefore, they exhibit functional isomerism with dienes. It is apparent that the particular alkyne can exhibit more one kind of isomerism. Fourth, ring chain isomerism. Alkynes also show ring chain isomerism with cycloalkynes. Terminal and non-terminal alkynes. Alkynes having the triple bond at the end of the carbon chain are termed as terminal alkynes. If the triple bond is present somewhere in the middle of the chain, the alkynes are termed as non-terminal or internal alkynes. For example, 1-butyne is a terminal alkyne while 2-butyl is a non-terminal alkyne. Geometrical isomerism not exhibited due to linear arrangement of atoms attached to the triply bonded carbon atoms. Alkynes do not exhibit geometrical isomerism. Structure of alkynes. Alkynes are marked by the presence of carbon-carbon triple bond in the molecules. The carbon atom involved the formation of triple bond are in the state of sp hybridization. To know the main structural features of alkynes, let us consider the structure of acetylene, the first member of alkynes. The carbon atom involved in the formation of triple bond make use of sp hybridized orbitals and two unhybridized p orbitals. The axes of the two sp hybridized orbitals are in such a straight line with the orbitals pointing in the opposite direction. The two unhybridized p orbitals are perpendicular to each other and also the sp hybridized orbitals. each of the formation which contain 1 electrons. In the forming acetylene, one of the sp hybrid orbitals of the one carbon atom overlap with of the second carbon atom to give rise to a sigma bond. The second sp orbital of each electron atom overlap a 1s orbital of hydrogen atom to form another sigma bond with each hydrogen. As the sp hybrid orbitals of each carbon lie along a straight line and the overlapping of these orbitals take place along their axis. All the 4 atoms of acetylene naturally lie along a straight line. In other words, acetylene is a linear molecule as shown with the help of the skeleton. The two remaining mutually perpendicular p orbitals of one carbon overlap sideways to the small extent which the similar p orbital of other carbon atom to form two sigma bonds in the planes and right angle to each other. If the electron cloud of one pi bond is considered to lie above and below the line joining the nuclei, then the other electron clouds lie in the front and back of the line. However, there is overlapping between the two pi bonds also, so that the four lobes of the two bonds merge to form a single electron cloud which is cylindrically symmetrical about the internuclear axis. It is obvious from the above discussion the carbon-carbon triple bond is made up of one strong sigma bond and two weak pi bonds. Its total strength is 828 kJ per mole as compared to 682 kJ per mole of a carbon-carbon double bond and 368 kJ per mole of the carbon-carbon single bond. Because of the smaller effective size of the sp orbitals and the additional sideways overlapping of the unhybridized p orbitals, the carbon-carbon distance in the triple bond is only 120 picometer. In comparison, the distance of the carbon-carbon double bond is 134 picometer and carbon-carbon single bond is 154 picometer. Similarly, due to the smaller size of sp orbitals, the CH distance is 106 picometer in acetylene and is shorter than C single bond H distance of ethylene, which is turn it shorter than C single bond with H distance in ethane. The presence of two pi bonds in the molecule makes acetylene and other alkynes very reactive. Method of preparation of alkynes. Method of preparation of alkynes can be studied under three categories. First, generation method of preparation of ethyne and higher alkyne. Second, special method of preparation used for ethyne. Third, preparation of higher alkynes from ethyne. First, general method of preparation. Like alkenes, alkynes can be prepared by the elimination reaction of hydrogen derivative as described below. First, dehydrohalogenation of dihalides. Dehydrohalogenation of dihalides by the use of a suitable base result in the formation of alkynes. The reaction takes place in two stages. The first stage yields a haloalkenes which get further dehydrohalogenated to form an alkyne. While the first step may be carried out with the alcoholic potash, the second stage generally requires the use of sodium amide, which is a stronger base. The dihalide employed may be vicinal or 1,2-dihalide to adjacent carbon as in the above example, or geminal or 1,1-dihalide halogens attached to the same carbon atoms as shown in the following examples. Second, dehydrohalogenation of tetrahalides. When heat with zinc dust, when 1,2,2 tetrahalides get dehalogenated to form alkynes. Tetrahalide with 2Zn reacts and gives alkyne and 2ZnX2, where X is an halide. This reaction is, however, not much of practical importance as halides are themselves generally prepared from alkynes. Second, special methods used for ethylene or acetylene. From commercial point of view, acetylene is most important alkyne as such many special methods are used for its preparation. Third, action of water on calcium carbide. Calcium carbide with reaction of hydrogen gives acetylene and Ca bracket OH2, which is known as calcium oxide. Calcium carbide required for this purpose is itself obtained by heating calcium oxide and coke in an electric furnace at 2273 Kelvin. Fourth, by dehydrohalogenation of halofoam. When heated with silver powder, chloroform or iodoform with acetylene. Fifth, controlled oxidation of methane at high temperature. Third, preparation of higher alkynes from ethane and lower terminal alkynes. Alkynation of sodium acetylides. This reaction involves the preparation of higher alkenes by treatment of sodium salt of acetylene or other lower terminal alkynes with the alkyl halide. Sodium salt of alkyne itself is obtained by the addition of sodium or sodium amide or alkyne. The alkyl halide is invariably a primary alkyl halide as used the secondary and tertiary alkyl halide most lead to side reactants. Mechanism. The mechanism of the reaction involves the nucleophilic substitution of the acetylide ion for the halide ion of alkyl halide. The halogen carrying carbon of alkyl halide acquires some positive charge or it due to the greater electronegativity of the halogen attached. This positively carbon charged is readily attacked by strong nucleophile acetylide ion with the simultaneous reaction of hydrogen ion. Physical properties. Physical state. The first alkynes are gases, the next 8 members are liquid, which while the still together one are solid at ordinary temperature. They are colorless and odorless. Only acetylene has slightly garlic-like odor due to the presence of phosphine and hydrogen sulfide impurities. Physical constants. The melting points and boiling point of alkyne increase gradually with the increasing molecule weights. The variation in the boiling points of isomerism alkynes are similar to those noted in case of alkenes. Even though the densities also increase with the rise in molecular weight, yet the alkynes are lighter than water. Solubility. Alkynes are insoluble in water but soluble in organic solvents such as ether, benzene, and carbon tetrachloride. Chemical properties. The distinguishing feature of alkynes in the presence of carbon-carbon triple bond, which is made up of sigma bond and 2 pi bonds. As in case of alkenes, the presence of pi bonds in the molecular makes alkynes highly reactive. As a result, they undergo many reactions including addition reaction, oxidation reaction, and polymerization reaction. Besides these, alkynes undergo certain reactions which are due to the acidic nature of hydrogen attached to the triply bonded carbon atom. Types of reaction. Addition reaction. When heated with hydrogen in the presence of suitable catalyst, alkynes can add on hydrogen to change in alkenes and ultimately alkenes. Alkyne with presence of H2, nickel, palladium and gives alkene, and with the same reagents it gives alkene. For example, acetylene with reaction with H2, nickel, platinum and palladium gives ethylene, and with the same reactants it gives ethane. Partial reduction. It is possible to arrest the catalytic reduction at the alkene stage of using a special catalyst palladium support on CaCO3 partially poisoned by lead acetate and quinotate and also known as Lander's catalyst or a nickel boride catalyst. Partial reduction can also be carried out by treating the alkyne with sodium or lithium or liquid ammonia. This is known as metal ammonia reduction or bridge reduction. Stereoselective nature of reduction. It is interesting to note that during controlled reduction, in the presence of Linder's catalyst or P2, addition of hydrogen takes place on the same side or face of alkynes and yields mainly cis alkene. On the other hand, metal ammonia reduction proceeds through addition of hydrogen on the opposite faces of alkyne and produces predominantly transalkene. In other words, the reduction of alkynes is stereoselective reaction. Mechanism of metal ammonia reduction. The mechanism of partial reduction of alkene by metal ammonia involves the initial donation of an electron by sodium to the triple bond. This gives rise to the intermediate, which is both a radical and an anion and is called anion radical. This anion radical abstracts a proton from ammonia to form a vicinal free radical. Donation of another electron from sodium form a transvicinal anion. The trans ion is sterically less hindered and more stable because in the bulky groups are further apart. Protonation of transvicinalic anion led to the transalkene. Electrophilic addition reaction. Due to the presence of two pi bonds in their molecules, whose electrons are easily accessible to attacking reagents, alkynes undergo many electrophilic addition reactions just as alkenes do. However, as expected, these reactions take place in stages involving 2 moles of addendum, 4 mole of alkyne. Comparison of electrophilic addition in alkenes and alkynes. Due to the presence of two pi bonds in the triple bond and one pi bond in a double bond, alkynes may be expected to be more reactive in their electrophilic addition reaction than alkenes. However, the actual position is that alkynes are somewhat less reactive than alkenes towards electrophilic addition. First, different type of hybridization. The triply bonded carbon atom in alkynes are sp hybridized while the double bonded carbon atoms in alkenes are sp2 hybridized. Now, the sp hybrid orbitals have greater s character and lesser effective size than sp2 hybrid orbitals. As a result of this, the electron pairs in the triple bond are more firmly held by the carbon atoms than the electron pair in a double bond in case of alkenes. Consequently, the electron pairs of a triple bond are less easily available to the attacking electrophilic reagent as compared to the electron pair of double bond. Hence, alkynes are less reactive than alkenes in electrophilic addition reactions. Second, cylindrical pi electron cloud. In the formation of carbon-carbon triple bond, the four lobes of two pi bonds merge to form a single electron cloud which is cylindrically symmetrical about the internuclear axis. In this cylindrical electron cloud, there is a greater delocalization of pi electrons than if the electron clouds of the two pi bonds had not merged together. Due to the greater delocalization of pi electrons, alkynes are more stabilized and undergo electrophilic attack less readily than alkenes. Third, less stability of intermediate ion. Another probable reason for the lesser reactivity of alkynes is that the intermediate ion formed in the first step of electrophilic attack on pi electrons is less stable than that of the formed in the case of alkenes. For example, the addition of hydrogen acid to an alkene proceeds through the formation of alkyl carbocation intermediate, while the case of alkynes, vinylic carbocations is formed as intermediate. Vinylic carbocation is relatively less stable than alkyl carbocation and is less readily formed. Therefore, alkynes undergo addition reaction less readily than alkenes. It may also be pointed out, unlike alkenes, alkynes do not undergo electrophilic addition reaction, but some of their reaction also involve nucleophilic addition reaction with electron-rich reagents. We now take up the important electrophilic addition reaction of the alkynes. Addition of halogens. Chlorine and bromine add onto alkynes to form dihaloalkenes and finally tetrahaloalkenes. Since bromine gets decolorized in this reaction, it can also be used as test for the presence of carbon-carbon triple bond in a molecule. It may, however, be recalled that bromination gets decolorized in this addition across a double bond. As such, reaction with bromine can merely indicate whether the carbon-carbon double bond or triple bond is present in a molecule. It is not possible to say specifically whether the bond is double or triple. Mechanism. The mechanism of the reaction involves electrophilic addition and proceeds through the formation of halogen ion as shown. In these, there are shown first stage and second stage of carbon in its compound. The above mechanism is in keeping with the fact that addition of hydrogen proceeds in anti-manner. As compared to alkenes, alkynes are less reactive towards the addition of halogens. This could be attributed to the following two reasons. First, intermediate cyclic halogen ion involved in the addition of halogen to alkynes is less stable and therefore more difficult to form than halogen ion involved in the addition reaction of alkenes. Second, in alkynes, the triply bound carbon atoms are sp hybridized, which hold the electrons more tightly so that the pi electrons are less easily available for the combination of electrophiles. Third, addition of hydrogen halides. The hydrogen halides HCl, HBr or HI add on the triple bond to give rise to haloalkene and finally dihaloalkene in accordance with Markovnikov rule. Free radical addition of HBr. In the presence of peroxides, addition of HBr to alkynes takes place against the Markovnikov rules. As already explained, anti-Markovnikov addition involves free radical mechanism. Addition of hypolluous acids when treated with an aqueous solution of halogen, a product corresponding to the addition of 2 moles of hypohalous acid is formed, then gets decomposed immediately to furnish a dihalocarbonyl compound. Addition of water. Hydration on treatment with dilute sulfuric acid in the presence of mercuric sulfate catalyst, alkynes get hydrated to form carbonyl compound. Hydration of acetylene form acetyl halide, higher terminal alkynes from methyl ketone while higher internal alkynes from other ketones. Alkynes on reaction with H2SO4 and HgSO4 gives unsaturated alcohol on further reaction with gives carbonyl compound. Acetylene with hydrogen ion gives vinyl alcohol and further reaction with gives acetyl halide. Propine with further reaction gives acetone. It may be seen that final carbonyl compound is formed through the intermediate formation of enol, that is, the compound in which double bond and hydroxyl group lie in the same carbon atom, which undergoes rearrangement to form the more stable carbonyl compound. It may also be noted that in case of unsymmetrical alkynes, addition occurs according to the Markovnikov rule. Mechanism. This is also believed to be an electrophilic addition reaction in which the step involves the formation of a complex between mercuric ions and a triple bond. Water then attacks the complex ion and this is followed by other steps. Addition of acetic acid. When treated with acetic acid in the presence of mercuric salts, alkynes form useful addition products. For example, acetylene forms vinyl acetate which is used in the production of rubber, and plastics. Nucleophilic addition reaction. Apart from electrophilic addition reaction, alkynes also undergo some nucleophilic addition reaction. This may at first appear to be rather surprising, but in view of decreased reactivity of carbon-carbon triple bond towards the electrophilic attack, it is reasonable to expect that alkynes may be susceptible to attack by nucleophiles as well. Like electrophilic addition reactions, nucleophilic addition is also takes place in two steps. In the first step, the nucleophilic attacks the alkyne to form a vinyl carboanion, which then takes up a proton to form the final product. Addition of hydrogen cyanide. Alkynes add on hydrogen cyanide in the presence of suitable catalysts such as barium cyanide or cuprous chloride. For example, acetylene adds an hydrogen cyanide in the presence of cuprous chloride catalyst to form vinyl cyanide, which is used in the manufacture of rubber. 8. Addition of alcohols. Alkynes can also add on alcohol in the presence of alkyne catalyst to form unsaturated ethers. For instance, when acetylene is passed into the methyl alcohol in the presence of potassium methoxide, methyl vinyl either is obtained. This is used for the manufacture of plastics. Polymerization reaction. Two or more molecules of acetylene or higher alkynes combine amongst themselves to form various polymers as illustrated below with the help of few specific examples. 9. Dimerization. When passed through a solution of cuprous chloride in aluminum chloride, acetylene dimerized to give vinyl acetylene. Vinyl acetylene itself combined with hydrogen chloride forming chloroplasts, which is used in the manufacture of rubber. Trimerization. When passed through a red hot iron tube, acetylene is partially converted into benzene. Similarly, methyl acetylene trimerizes into the presence of sulfuric acid in the presence of sp3 trimethylbenzene or macetylene. Tetramerization. Acetylene undergoes tetramerization under high pressure and the presence of nickel cyanide catalyst to form cyclooctatetrene. Oxidation reactions. On oxidation with different oxidizing agents, alkynes form various oxidation products as illustrated below. Hydroboration oxidation of alkynes. When treated with diborane, terminal alkyne undergo addition in two stages, forming firstly a vinyl borane and finally a gem dipro derivative. It is not possible to stop the reaction at the stage of vinyl borane. Terminal alkyne further gives vinyl borane and then gives gem dipro derivative. If in place of diborane, a bulky sterically hindered borane such as bis 1,2 dimethylpropyl borane, commonly known as dicyamylborane, is used, reaction can be stopped at the vinyl borane stage for all alkynes, whether terminal or internal. Oxidation of vinyl boranes. The vinylic boranes can be oxidized with H2O2 in the basic solution to form aldehydes or ketones via emolic intermediates. Compare with the hydroboration oxidation of alkenes. Oxidation with potassium permanganate. Oxidation of alkynes leads to the formation of different products depending upon the nature of oxidizing agent and reaction conditions. We will now consider the oxidation of alkynes with alkaline potassium permanganate. First, oxidation at room temperature. Upon oxidation with alkyne potassium permanganate at room temperature, alkynes are oxidized to 1,2-diketones or carboxylic acid. Oxidation at higher temperature. In the oxidation of alkynes with hot potassium permanganate, the triple bond is completely broken, leading to the formation of carboxylic acid and carbon dioxide depending upon the structure of alkynes. As in case of alkenes, the pink color of KMNO4 is discharged in these reactions as well. Therefore, the discharge of pink color of KMNO4 is used as test for unsaturation. Oxidation reactions of alkynes with ozone as potassium permanganate are used for the structure of determination of alkynes. Combination Combustion. When burnt in air or oxygen, alkynes get completely oxidized to form carbon dioxide and water. The reaction is highly exothermic. For instance, combustion of acetylene yields approximately 1305 kJ of heat energy per mole and produces flame temperature of more than 3275 Kelvin. Acidity of alkynes. A very predominant feature of acetylene and other alkynes have a hydrogen attached to the triple bonded carbon atom and is acidic nature of such as hydrogen. Therefore, unlike alkenes, terminal alkynes behave as weak acid. Cause of acidity. The acidity of terminal alkynes can be explained as follows. First, hybridization. As already stated, triply bonded carbon atoms of alkyne use two sp hybrid orbitals, each of them in the formation of sigma bonds. As such, these carbon atoms of alkynes have greater s character as compared to doubly bound carbon atoms of alkenes and single bond carbon atoms of alkenes. Now, the s electrons on the average are held more closely to the nucleus than p electrons. Therefore, the sp hybridized carbon atom of alkynes have greater attraction for electrons, or in other words, they are more electronegative than sp2 and sp3 hybridized carbon atoms of alkenes and alkenes. Hence, triple bond C bond of alkynes has greater degree of ionic character than the double bond carbon atom of alkenes and single bond carbon H bond of alkenes. That is why the hydrogen atom attached to triply bonded carbon of tendency to release H plus ion. Stability of alkynyl ion. Since sp hybridized carbon is relatively more electronegative, it can accommodate the negative charge better. As a result, the alkynyl anion formed after the removal of proton from terminal alkyne is more stable than the anions formed from the removal of a proton from an alkene or an alkane. Hence, alkynyl ions can be relatively easily formed. It may be noted, however, that the acidic nature of acetylene and other terminal alkynes is very weak, even weaker than water. Thus, like water, they do not turn blue litmus red, but acetylene and other terminal alkynes do undergo the following distinguishing substitution reaction due to the presence of acidic hydrogen in them. Formation of alkali metal acetylides. Acetylene and higher terminal alkynes react to alkali metals to form salts and liberate hydrogen. For example, acetylene reacts with sodium to produce sodium acetylide to involve hydrogen. But sodium acetylide is decomposed even by water to form sodium hydroxide and regenerate ethylene. This is because a weaker acid is always displaced from its bisalt, a stronger acid. Formation of heavy metal acetylides. Acetylene and other acidic alkynes react with heavy metal ion, particularly Ag ion and copper ions, to form characteristic acetylides. These acetylides is quite explosive when in dry state. Since the acetylides are easily decomposed even in weakly acidic solution, their formation and subsequent decomposition is utilized in the separation and purification of acetylene and other terminal alkynes from gaseous mixtures. The formation of acetylides can also use for distinguishing terminal alkynes from other hydrocarbons and even from distinguished alkynes, which do not undergo this reaction. Synthesis uses of alkyne. Apart from its well-known use of oxyacetylene flame employed for welding purposes. Acetylene also find many synthetic applications. However, the higher alkenes are used only to very limited extent, mainly because of their known availability in larger quantities. The main synthetic uses of alkynes are therefore described below. The reference to acetylene. The important substances synthesized from acetylene are: first, acetal, aldehyde, acetic acid, ethyl alcohol, acetone, benzene, etc. Second, industrial solvents such as Vestrone and Vestrosol. Third, vinyl chloride, vinyl acetate, and vinyl ether used in the production of plastics and artificial rubber. Fourth, acrylonitrile used in the production of synthetic fibers and rubber, etc. Fifth, chloroprene and butadiene used in the synthetic rubber industry. Sixth, tetrahydrofuran, which is important solvent in organic chemistry. Seventh, lewisite, beta chlorovinyl dischloroarsine obtained by reaction between acetylene or arsenic tetrachloride, which was used as war gases. Thank you.